All right, here I have an object that I know the mass of, 0.5 kilograms. It's half a kilogram, and it's sitting on a 15-degree ramp without slipping. So I'm going to start out by drawing my ramp and drawing this object that is sitting on the ramp. And I know a couple things about this object, and I'm going to solve as I go because I actually know the mass here. So I'm going to start out by finding the force of gravity. Force of gravity is just mass times gravity, mg. So I've got 0.5 times 9.81, and I'm getting 4.905 newtons. All right. Force of gravity can be split up into two components here. A component of the force that is perpendicular to the ramp, F perpendicular, and a component of the force that is parallel to the ramp, F parallel. These form a right triangle that looks something like this, where the right angle is between the perpendicular and the parallel sides. So I'm just going to label this F perpendicular, F parallel, F parallel, and force of gravity, Fg. And the angle that's given to me in this problem, 15 degrees as the angle of the ramp, is the same thing as the angle here in this similar triangle, the angle between Fg and F perpendicular. That's 15 degrees there as well. Which means I can solve for F perpendicular. F perpendicular is just equal to the force of gravity times the cosine of 15. And the force of gravity we just found was 4.905 times the cosine of 15 gives me a perpendicular force of 4.74 newtons. The parallel force is the force that is, or the one that is opposite here. So opposite over hypotenuse is the sine. That simplifies down to F parallel is equal to Fg times the sine of 15. 4.905 times the sine of 15 gives me 1.27 newtons. All right, I'm going to take these and redraw a free body diagram that is a little bit cleaner for me. So here's my object. I know that my perpendicular force is 4.24 newtons. I know that my parallel force is 1.27 newtons. I know also that this object is experiencing a couple other forces as well. It is experiencing a force that is the normal reaction force of the surface that is pointing perpendicular. So that's R. And R in this case has to be equal and opposite to our perpendicular force. So that is 4.74 newtons. I also have a force that is pointing up the ramp. That is my force of friction. Now in this case, I know that this object is sitting there without slipping. If this object is sitting without slipping, it means it's not moving. If it's not moving, it means there is no acceleration. If the acceleration is 0, it means the net force has to be 0 as well. So all of these forces need to be canceling. Just like R canceled out with the perpendicular force, FF must cancel out with our parallel force. So that is 1.27 newtons. This problem is asking for us to find the coefficient of static friction. If we are talking about a coefficient of friction, we know we need to use this equation. FF is equal to mu times R. This is our equation that uses coefficient of friction to relate some force values. So if I rearrange that and solve for mu Ff divided by r, it's going to give me 1.27 divided by 4.74. 1.27 divided by 4.74 will give me a value of 0.268. That is a unitless number as our coefficient of friction. So again, what we found here is use the mass to find the force of gravity, use the force of gravity to find our components of the force, use those to make a free body diagram that we knew had to cancel out. So all these equal and opposite forces allowed us to find out R and the force of friction, and those were the two values we needed to solve for mu, and then ultimately that gave us 0.268.